So 2A, you've got to get the acceleration. Stephen, we're filming, right?
Yes.
To get the acceleration at 7.5, you're going to find the derivative of the velocity, which is negative 0.1 miles per minute squared. Everybody okay? All right, 2B, I want you to find the integral of, what function is this?
Absolute value of velocity.
Absolute value of velocity. We have a faster way to say it, which is speed. I'm asking you to find the definite integral of speed, which means anytime you had a negative area, it's going to become positive, and if all goes well, 1.8 miles is the answer. What does that mean, though? What does that mean in terms of this problem? Myra, what does that 1.8 miles represent?
From t equals 0 to 12 minutes, the total distance traveled.
Okay, from t equals 0 to t equals 12 minutes, this is displacement or total distance?
Total distance.
It's total distance. If you're finding the area underneath the speed curve, it's total distance. Yes, sir?
Is it fine to just say distance instead?
One more time?
Is it fine to just say distance?
traveled.
It would be better to use the word total distance traveled. Okay, I'm not going to take a point off for that, but that's a good question. Total distance. Let's use the words total distance and displacement and not get them confused. All right, but so from t equals 0 to t equals 12 minutes, Karen writes a total distance of 1.8 miles. Done. All right, 2C, when is Karen turn to go home? At t equals 2 minutes, we can see that because the velocity changed from positive to negative. She was going forward, now she's going backwards. 2D, Larry's distance to school is 1.6 miles. And if you've got the graph in front of you, unfortunately, I don't have the graph in front of me. If you graphed, was it Larry? All Larry's curve does, we go from 0 to 12, we're positive, it's above the x-axis the whole time. Aaron, did you find your wallet?
Yeah.
Okay, good. All right, so I'm just going to find the area under the curve. In a situation like this, when you calculate the integral of w of t dt, displacement or total distance traveled?
Displacement.
Displacement,
Yes.
total distance traveled, or trick question?
Displacement.
If you look at the setup, the right thing to say here is displacement. If you look at the graph, there's something here that tells you I can actually get away with saying total distance traveled.
Oh.
Stephen, why can I get away with saying total distance
Oh,
traveled?
because the area is positive.
The area is all positive. There's no negative area. All Larry does is go in the forward direction. So whether you refer to it in this case as displacement or total distance traveled, they're going to mean the same thing. All right, Karen's distance to school. Now the mistake that a lot of folks make is they do like the integral from like 0 to 12. But what you've got to keep in mind is Karen actually spends some time going to school, then she turns around coming back, and then starts to go forward. So her distance from school you can actually calculate by just doing an integral from 5 to 12 and get 1.4 miles. So Karen lives closer. In terms of the physics, is everybody feeling like really good about this? We get this under control? Good. All right, moving on. Okay, problem number 3, maybe a bad choice for me to use the light green here. With all of these, all you needed to do is tell me what it meant. So the integral from 10 to 15 is the change in temperature from t equals 10 to t equals 15. 350 plus the integral from 0 to 60 is not the change in temperature. That's like the integral from 0 to 60 is telling me change in temperature. That 350 is like the starting temperature. So if I take my starting temperature plus the change in temperature, what I'm going to get is what's the temperature at 60 minutes. T prime is going to be the rate of change of the temperature at time t equals 10. Number 5, that's in here somewhere. It's in green again. All right, number 5, part A. Looks like 409.980.
I got 161.
I got
You
one
got
six-
161?
161.
3 is 110.
Can I have a question? All right. Oh, bummer. I changed the numbering. That's what happened. So number 5, this is one about like the cars.
Yes.
Okay. So I've got in A, 2,687.750 cars.
I see what
No. Lewis is like, no. In B, I've got 2,562.250 cars.
No.
In C, I've got 2,660.500 cars.
No.
And in D, I've got 2,324.500 cars.
No.
Well,
I doubt that I'm wrong all 4 times.
you mean. I know why we did it on the same. We put 15 minutes instead of 140. That's a mistake.
Okay.
Yeah, because I did out of 15.
Right. The units for the 1,044. Hold on, I want to get that. Thank you. What are the units for the 1,044? Look at the table. What are the units for all of these values? Cars per hour.
oh,
Cars per hour. So I bet what all the friends are doing is you multiply by 15. The problem is the units aren't going to work there. That 15 is minutes. This is cars per hour. You got to get the units to be the same. So did anybody get 2,687? I bet so then everybody has this number times 60, which is like 160 some odd thousand. And then I bet you're going to have this number times 60, which is like 159,000. This number times 60 is another 159,000. This one times 60 is about 139,000 and some odd. Yeah, that's what's going on there. Okay, here's is everybody okay with why the half and the quarter, not 15 and 30? Okay, good. All right, let's just end scene there. So you guys can put that away. Make sure you learn from that mistake, please. Tonight's homework that you're going to work on, I strongly get it done tonight. I know there's no school Friday, there's no school Saturday, there's no school Sunday. I can't change those things. Just tell yourself, I'm going to get this done tonight, and enjoy Friday, Saturday, and Sunday. Okay. The quiz is a total of 30 minutes. Let's take a look at it so everyone knows what you're looking at. Thanks, Lewis. The first 8 questions are calculator active. Calculator active here. You've got 8 questions. You've got 20 minutes. That might even be more than enough time. The last question is calculator active. It's a word problem. If it's a word problem, all of your answers are going to involve units of some sort. Please be careful. Do not spend any more than 30 minutes on this, no matter how much you might start to panic. Everybody okay? Carmen and Celeste, we'll talk about the quiz when you come back next week. I miss at least one of you, maybe both, I'm not sure yet. All right, everyone's good with the quiz? All right, so why don't you guys take out your calculators. We're going to be very calculator active today. I am really excited. There you go. Very excited about the integral. I think the definite integral it's just one of those things that every time I write it, it just makes me happy because people walk in and they're like, what is that? What does that even mean? This just screams, I'm in a calculus class. So, Andrew, can you read this for me?
The definite integral.
Definite integral.
The graph f of x.
Of the graph of f of x, or just of f of x, that's fine. Keep going.
On the x-axis
With respect to x.
between a to b.
From a to b. It's the definite integral of f of x with respect to x from a to b. Everybody okay?
Yep.
And Giselle, what does it actually mean though? He read it, but what does it mean?
It means to find the area bounded by the graph of x.
Okay, you get the area bounded by the graph of f of x. That's one thing. There's 3 more.
The x-axis.
Have to include the x-axis here.
And the vertical lines at x equals a.
The vertical lines, x equals a and x equals b, and I would hope that everybody is 100% with this, right? Okay, good. Now here's the thing, and I got some pushback from the College Board on this. I kept saying this is what the definite integral means, and I want to clarify. This area is one way. to interpret the definite integral. It's one meaning, one interpretation, one application is area. There's others. So for example, if I said like the integral of v of t dt from a to b, you wouldn't tell me area. It's an application question. This means something different here.
Displacement.
What does it mean? Displacement. I need to be more specific though. The word displacement isn't enough.
Displacement over A.
It's the displacement from A to B, and there are going to be some kind of units, right? So like, make sure you get that in your notes, and I think there's even space over there for you. So this just means displacement from t equals A to t equals B. Well, that's like one way we've seen it. We've also seen the integral show up over there. Different meaning here. Aaron, what's the meaning here?
That's just the total distance
Okay, this is total distance, but be specific.
from A to B. From T
It's
equals
total
A.
distance traveled, right, from t equals A to t equals B. Love it. Well, there are other things. We saw in, like, the swimming pool problem, right, that you guys did, was that Monday night, maybe? In the swimming pool problem, we had, like, the function had some other meaning. The function r of t, what was this, like the rate that water, what was the water doing in that swimming pool problem?
Leaky.
Right, the rate that water leaked out in, let's call it gallons per minute. I think that's what the units were. The units for r of t were gallons per minute. Everybody okay?
Mm-hmm.
The units for time are
Minute.
minutes. So the units for this definite integral, when I put the whole thing together, if r of t is measured in gallons per minute, and time was being measured in minutes, then the definite integral was getting measured in gallons. And the meaning was, if r of t was like the rate, and I really want to like hammer this point home, r of t is rate. It's a how fast, right? It's how fast water leaked out. The definite integral was not how fast, but how much. How much water leaked out from t equals A to t equals B, and we were measuring in gallons. A rate function is always going to tell you how fast something is happening. How fast is something increasing or decreasing? The definite integral is going to tell you how much is the change, and we also call it net change. Everybody okay? Let's go back to the amusement park problem. Remember the amusement park, we had people that were coming in. That was like some function E of t. We had people that were going out. That was some function L of t. Both of those are rate functions. So they're how fast something was happening. So if it was like E of t from, I don't know, let's call it like t equals 0 to t equals 6. If E of t was how fast, then the meaning of the definite integral has to be
Of U of T, how many people enter?
right. E of t is how fast people are coming in. The definite integral was
How many people?
how many people came in, but be specific.
From
How many people came in
From
T equals 0 to T equals 6.
from t equals 0 to t equals 6? If it was the other function, the leaving function, when you integrated L of t, it was how many people left from t equals 0 to t equals 6. Big picture? We're good? All right, so with that said, it's time for the push. What I want you to do is look at problem number 37. I want to give you guys a chance to read through this, mark this up, make sense of it. If you want to graph it on the calculator, graph it on the calculator. Palamon, do you mind driving the calculator? Testing my peripheral vision. How close to my peripheral vision? Oh, okay. Did anybody do the bonus assignment? There's the bonus assignment, finishing off that definite integral. Okay, half of it. So we're not going to call it a bonus assignment, we'll just call it a bone assignment. You did half, I'll call it half. Don't think about it too much. All right. So a cup of coffee at 90 degrees Celsius put into a 20 degrees Celsius room when T equals 0. Temperature is changing at this rate when T is measured in minutes. My first question for you all has nothing to do with calculus. It's a science question. Let me get into a better position here. What's happening to the cup of coffee? What has to happen to the cup of coffee? Don't overthink it. Trust your science here. The cup of coffee gets colder. What's the initial temperature? 90 degrees, and it has to get colder. Now, if I think about the graph, if what I'm graphing is the temperature of the coffee, like here's the time, here's the temperature, you guys told me that, you're told in the problem, what's the initial temperature? Was it 90?
Yeah.
Okay, so at time 0, the temperature of the coffee is 90 degrees, and the temperature gets colder, and everybody seemed really fine with colder. How much colder? Does it get down to 0?
No.
Does it go negative?
20 would be the limit.
How much colder? Think about the science. Think about the situation. I've got my cup of coffee at 90 degrees Celsius. I put it in this room. Clearly it gets colder. How cold?
Oh, just give it to.
Right. The temperature of the room is 20 degrees Celsius.
It can't go below that.
You can't actually get below 20 degrees Celsius.
Temperature of the environment.
Right, this isn't a calculus conversation anymore, it's a science conversation. We're talking like transfer of like heat energy. So if the temperature of the coffee actually starts at 90 degrees Celsius and the temperature of the room is 20 degrees Celsius, what's going to happen with the temperature? Just think about what would the graph have to look like. You guys said decreasing, but it's going to decrease in a really specific way.
Concave down.
Concave down would like look like that the whole time?
Wait, no, concave, I mean, no.
Yeah.
Or is it
Wait.
I agree we're going to have some decreasing.
I don't buy that.
But what happens over time? As time passes, what has to happen to the graph?
It'll approach 20 degrees Celsius.
It's going to approach 20 degrees Celsius. Like to get to 20 degrees Celsius?
No. Well, it could. It could.
And the actual answer there is it never actually gets to 20 degrees Celsius. The coffee always has a little more heat energy than the room
Oh
does.
yeah, because there'd be no heat transfer.
Right, you've got this like, it's like kind of going back and forth. What's going to happen is what I would expect is actually like a horizontal asymptote of some sort with the temperature. That's like the science behind what's going on. I want to play around with the calculus. These first couple of questions I think you guys are going to be just fine with. So part A, in the context of the problem, explain the meaning of the expression integral from 0 to 10r of t dt. Then, using your calculator, determine the exact value. See what you can do with A and B. We'll talk in 2 minutes. And Palomon, if you could maybe graph that function. Stephen, can all the friends see the stuff on the sideboard?
Yeah.
Okay.
Instead of total temperature decrease from T equals 0 to
In part A, I want your explanation of this definite integral. I don't care about a number. Palomon, if you could graph the function. The work that you're doing is good for part B, but I want to get the graph of the function there as well. Nice. How are we feeling about the one? Nice, nice, nice.
Represent how much the temperature
All right. All right. R of t. The way I think about this, especially as a new calculus person, R of t is measuring what? It's the rate. It's how fast, right? So it's a how fast what's happening? It's how fast the temperature is decreasing. Okay, so if R of t is how fast the temperature is decreasing, then the integral Lewis, what's going to have to happen with this Lewis? What's going to have to happen with this Lewis integral? What's going to have the meaning of this definite integral, Lewis?
Is the temperature at, is like the amount, like, you know what I mean?
R of t is how fast the temperature is decreasing. The integral is, just switch how fast to how much. So what does this integral mean?
How much the temperature.
How much, okay, give me the whole thing.
How much the temperature decreases.
How much the temperature
After
decreases, be specific.
after at 10 minutes. During 10 minutes.
From, you're over an interval. How much the temperature decreases from t equals 0, 0, 0 to t equals 10 minutes. Now, I like that answer. I don't love this answer. We're missing units here. There's an important unit that wasn't brought up. What you got?
In degrees Celsius.
This is in degrees Celsius. And if you're not sure where the degree Celsius is coming from, the units for R of t,
Oh, degrees Celsius.
those are not the units for R of t.
Degrees
Degrees
Celsius.
Celsius per minute.
It's degrees Celsius per minute. Then we look at the dt, the like with respect to, what am I measuring time in? Minutes. I'm multiplying those two together. That's why it comes out as degrees Celsius. We good? All right, go get me part B. Is it negative? Negative 44. Does that make sense that it's negative? Right, that answer comes out to be negative. It has to be because you know the temperature is cooling. So Ale, what do we get for answer?
Negative 44, 22, 48.
Units?
Degrees Celsius.
Has to be degrees Celsius.
You don't need to put 3 decimals.
But
You don't have to, right?
I don't have to, I don't.
No, okay, set right to
Oh, round your answer to the nearest whole number. I thought you were just like making some really bold, stupid statement like, we don't write to 3 decimal places anymore. All right, C, express the definite integral. Oh, I love this. As the sum of an infinite number of rectangles using the right endpoint method. Aaron, you know I'm coming over to you for this one. In D, using the trapezoid method with 4 trapezoids of equal width, estimate that value. I'll let you guys play around with that for a little bit. You okay back there?
Yes.
Okay. Yes, sir.
Not sure this is the correct way of saying it because
Yeah.
at the right point it would start like this. Like the right side, meaning you would actually not start at 0, you start at n, I guess. So it'd be 0 plus n where you start.
No, and you're using n in the wrong way. N is the number of rectangles. What you need to be thinking about is the width of the rectangles.
So n divided by n.
There you go. Alright, so you've already got an interval. You can write 0 to 10. And if you're not 100% on this, okay, we're going from 0 to 10. That's the interval. I need to partition the interval. How many rectangles? Ultimately an infinite number, but I can't draw an infinite number, so what you start with is n rectangles. You're like, okay, here's my here's my partition of n rectangles. Well, if I've got n rectangles, I need to figure out how wide each rectangle is.
10.
And the width, right, I'm always going to do it this way. Like delta x is going to be 10 minus 0 over n, 10 over n. I'm starting at 0 in this case. That first rectangle starts at 0 and it ends at 10 over n. The next one starts at 10 over n and it ends at, what is that, 20 over n? So, right, I'm just going to keep adding 10 over n. It's that pattern that like makes everything come together. Pretty good. Right endpoint method, if I think about my rectangles, yes, they're going to go below the x-axis. Yes, that might mess up my head a little bit. But these are my rectangles. 1 rectangle, 2 rectangles, 3 rectangles, all the way out to the nth rectangle. If you need to see the pattern, go through. How wide, how tall, how wide, how tall, how wide, how tall. What's going to happen, and if you're in like part C right now, the integral from 0 to 10 r of t dt, well, we're going to do what? 10 over n, r of 10 over n. 10 over n times r of 20 over n. All the way to the last one, 10 over n, r of 10 times n over n. But really what you want to do is you want to collapse all this down. There's a pattern here. I'm multiplying by 10 over n all the way through. I'm doing r of 10 over n, r of 20 over n. If I'm going to use my sigma notation, I need a counter. K goes from 1 to n, so I get all n rectangles. Each rectangle has a width of 10 over n. The height of each rectangle is going to be r of, here's where things get a little tricky, r of the width, 10 over n, times k. And because I'm starting over here at 0, I don't need to do like 1 plus 10 over n or negative 3 plus 10 over n. It's just 0 plus 10 over n times k. I like this, don't love it. I need that limit as n approaches infinity. Okay, Palomino, you've got a question, and David, you got a question. How are we doing with this? How many guys were able to go like basically straight to the setup? Right, like there's a pattern here. I'm going to keep asking you this question so you get really good at the setup. Keep going. David, you had a question. Palomino, you had a question.
How you will get 10 inside each right outside.
Say it one more time.
You know how the pigmentation you will take in?
The 10 over n?
You can have it outside the floor, right?
I can have it outside of that summation. Why?
Property.
It's a property. The thing is 10 over n is a constant.
All right.
Once you determine the number of rectangles, 5 rectangles, 100, 1,000, 10 over n's constant, so I can pull it out in front if I wanted to. I could also put the 10 over n over here if I wanted to. Palomino, what was your question? Okay, so you guys just keep going. You don't need me. Keep going. And there's some questions on the back that I want us to look at. Is this corrections? Original work?
Oh, that was original work.
That was original
Yeah.
work there. Okay, so this is like a full floor. I was just confused because normally when people switch colors.
Oh, yeah.
Over here, is this corrections or is this original work?
That's original. I did this part too. This is the correction right here.
I'll fix that.
Oh, you were doing it about 2 points. I was saying like the changes to.
All right, Palomino, can you start working on the calculator there to show us your area? Zero to 10, r of t dt. We're doing trapezoids this time? Okay, if I'm going to go from 0 to 10, 4 trapezoids of equal width. How wide is each trapezoid going to be? It's going to be 2.5. Okay. Now, if you want to use your sigma notation, I mean, feel free, but honestly, you just need to be able to type this into the calculator. I'm going from 0 to 10. The width is 10 minus 0 over 4, 2.5. So 0, 2.5, 5, 7.5, and 10. Area for the first trapezoid. Can I get some brave soul? How are you going to find the area of the first trapezoid? What's your setup?
Oh,
David, and then you're frozen for a little bit.
the first chapter is gonna be 2.5.
2.5.
Parentheses, R of 2.5 plus R, no, R 0 plus R.
Yeah, okay. There's also something else here that I don't like. There's something that I'm really worried about. 2.5 times R of 0 plus R of 2.5 times a half. Okay, so you're kind of like living in backwards world right now. Right, because normally, just what I would normally do, I'd put the half first, right? Because it's like 1/2 base 1 plus base 2 times the height. I'd put the 1/2 in the front. That's why I worried when you put the 2.5 first and the 2.5 at the end, but we all know, same thing. First trapezoid, second trapezoid, same darn thing. Third trapezoid, same thing. Fourth trapezoid, same thing. There's a faster way to do this. Did any of you guys go with the faster way? Lewis went with the faster way? Right, you could just keep doing this sum. Myra, do you remember the faster way?
I was going to, I multiplied the R, 2.5, 5, and 7.5.
You said, okay, so you said you take the R of 2.5 and then what?
Oh, did I tell you the whole thing?
That'd be nice.
Okay. So 1/2 times 2.5.
Okay, so 1/2 times this 2.5,
And then R of 0
R of 0
plus 2R of 2.5.
plus R of 2.5 twice,
And 2 times R of 5
2 times R of 5,
plus 2 times R of 7.5
yep,
plus R of 10.
plus R of 10, and then close it off. That 1/2 is a common factor. I see you. Give me a second. That 1/2 is a common factor. I can pull that out. That 2.5 is a common factor. I can pull that out. And this doubling of your bases happens at, like if you think about your trapezoid, it's going to happen over like here. This guy gets doubled because you're counting it as the second base on the first trapezoid and the first base on the second trapezoid. This guy gets doubled. This guy gets doubled, but the last one and the first one get used just the one time. Steven?
Shouldn't it be squiggly since it's a
Shouldn't it be squiggly? You mean my handwriting should be squiggly?
No, like you know where it says equal.
Yes, I know what you meant. Okay, I was just hoping that with your big brain you'd come up with something better than squiggly.
It's an estimate.
You might call it
Estimate. Approximation.
an approximation. Yes, it's the squiggly. All right, and according to ILA, negative 44.478. Can I get some confirmation on that number?
It's on the screen.
Negative 44.478 degrees Celsius. Really close to what we had before.
Yes.
The trapezoid method is always a really good, really strong estimate. All right, let's look at E, F, and G. Determine the temperature of the coffee at time t equals 10 minutes. Just gonna let you dangle with that one for a little bit. What's the temperature of the coffee at time t equals 10 minutes? More than anything else, I'm interested in how you would set this up.
Yes.
Trust your science instincts here.
Wait.
Yeah, you just subtract.
You just subtract that from mine.
It's supposed to be at, but then.
I was like, wait.
Yeah, keep going.
I was like, it's the total.
That'd be a tip, right?
You already have the-
Love it. Give me a number though.
Degrees Celsius.
Correct.
Does that feel right? Trust the instincts. Just about everybody is doing something with the integral from 0 to 10 of R of t dt. And keep in mind, what does that mean? That means how much did the temperature decrease by? I'm asking you what's the final temperature? The thing that you need?
That's 90.
It's the 90 degrees. So it's the 90 degrees plus the change equals, what is this, 45 point, what are we getting?
45.7516.
45.7516, Palamon, are you gonna,
No, that's what's solid.
that's kind of why you're there.
Then you just extend it.
Okay, great, so you just decided to like this is next.
I didn't do anything. I didn't touch it.
I know you didn't do anything, that was the problem.
David, that's your job.
Alright, let's figure that out in a little bit.
Hendrickson unplugs it.
Here's the thing, there is a seed that I am planting, I don't know that I'm planting it very well right now. The definite integral is telling you how much the change is, right? How much the temperature decreased by. So this guy here represents your total change in temperature. Oh, thank God, we're back.
We're still not done though.
Okay, the 90 is your initial temperature, right? It's your start. Your initial temperature, if I add that onto like what's the total change in temperature, what you're going to get over here is your final temperature. However you want to spell that there. So with that in place, get me part F. And then you guys are going to practice with some multiple choice questions.
Ooh, this is cool.
So do I just leave you? Well,
Not
so
I wanted to know the temperature of the coffee, the actual temperature of the coffee at time t equals 10. I started with my 90. I figured out what was the total change, and that's going to give me the final value. But I want this now for any particular time. Like if I said, hey, how would I figure out the temperature at t equals 15 minutes? I have the same starting temperature. Difference is now I'd let the temperature change from 0 to 15. And this is going to give me the final answer. So if I want to look at any time t, if I want to come up with like a general equation, it's going to be 90 degrees plus the integral from where to where. The 90 degrees is my constant, like this is my starting point. I want to come up with an expression for any time t that you're interested in. 5 minutes, 15 minutes, 37 minutes. You can integrate from 0 to t. R of t dt. And that would be a way to figure out the temperature at any particular time. So Lewis says, hey, but I'm interested in what's the temperature after 15 minutes? 90 plus the integral from 0 to 15, R of t dt. One small notational thing, and this is like I'm going to be really picky about this. The College Board is more forgiving than I am. I think it is confusing to use t in so many places. You're identifying like a particular time t that you're interested in. You're like, this is like a fixed value of t. If you're going to use t here as your upper limit of integration, my recommendation is don't use t in here. So use something else. Use anything else. Just don't use t, because we need t to be a specific t. Just give me a different variable. Let's avoid using r, because that's the name of the function. So maybe you want to just call this r of x dx. Or you want to call it r of a dA. You want to get really fancy and kind of start getting ready for like spring semester, r of theta d theta. Which doesn't really make any sense since we're not talking about angles, but I'm just saying it's coming. R of x dx is just fine. Everybody good? Palamon, you're good back there? Alright, Palamon, why don't you return to the land of the living? We're not going to worry about part G because I think you guys are going to be just fine with part G. What I'm going to ask you to do is go backwards to pages 35 and 36. There are 6 multiple choice questions. All of these have shown up on past AP exam questions. These are all fair game on the take-home quiz you guys are going to do today. I'm just curious to see what you guys can accomplish in the next 10 minutes. Definitely feel free to use your notes. If you have any questions, you can ask me.
I thought this was so.
Let him put it in the writing.
He knows why I already did.
Ah, there you are, Knucklehead. So you did these. Did you do all of them? Okay. Excellent. Thank you for not being a total slacker. All right, then what I want you to do instead is,
Whoa.
I said for number 2. It says total distance you need here, and this one is. Yeah, but. You see, the thing is. I'm back now. Ain't bad. Don't worry about it. First, let's say I did this in my that's all I was saying. I was like 3-6. I was like, wait, how did it that's all that Wait, which one?
Feel good about that. You guys being the first. Feel good about that. Friends right here. I felt really good about that. So tell me, what's your plan? How are you going to determine the total distance? Look at the area. You're right to look at the area. Well, you usually find this right. Total distance traveled and you think about the area below the x-axis. So number 3. What's the problem with 3? I think you're making an assumption that it's true.
Oh,
5 half times 20. Why 5 half times 20? Bye-bye. All right, for all the friends on the other side of the camera, hopefully for number 1 you have B, and number 2 you have B. And number 2, total distance, you need the area underneath the speed curve. So the area underneath that, the area of the triangle over there, you're going to have to count it as positive.
did you just find the area from 7 in here? Like this? This is 2 and 3.
Okay, but here's,
So it's right
it's
there.
gonna,
and it's gonna
I
be
understand, I'm sorry, I understand where the
Still
48
uniform.
is coming from now.
So
Here,
what's
okay.
What's the width here?
Finding the difference between 2 and 5 is telling you how long the interval is. But what's the other thing that you need to do to figure out area? You need the height.
So what's here?
The height's not gonna be changed a lot. Because you've got your x-axis over here, you've got like a point over here, you've got another point over here. Right, you're not measuring from like how high was I to how high do I need to go. You're measuring from your x-axis up. So you have a width of 3. And what's the height? It's f at 5 because it's the right end.
So it'd be 28.
Yeah.
Oh, that makes sense.
Right?
So it's 3 times 28.
Yeah.
34.
So we have
And then
84.
Okay.
And just be careful here because you no longer have a uniform partition, right? You're not looking at equal distances.
Changing the first number.
Yeah. And so because you don't have equal distances, you can't do any like fancy factoring. Fancy factoring is gonna mess you up.
Yeah, I'm so used to actually doing all the work out, which is why I saw the picture
You're used to doing all the work, that's
Hey.
funny.
I don't, I was, before I knew you could.
I'm used to doing all the work like every 3rd day or something.
You guys see, right?
What'd you guys get for number 3? D. Does that feel pretty good? Good. All right, number 3 back here, how do we do? 374, so D.
Good. The same thing as-
Good. Friends on the side of the camera, number 3, D. The question that just about every single person and their mama gets wrong is number 5. I'm not going to tell you what the answer is yet, but if you haven't made it to number 5, get there soon. Nope. Still no. Yes.
Yeah, no, we just stay with. Trappers.
Yeah, that means you add to, which is what I did, which is how it's actually.
Wait, were you asking me about number 4 or number 5? Oh, I thought we were talking about number 5. Number 4 is C.
Then you divide it up. If you got 320, right? You divide it up.
No, so, wait, it's not just.
Yeah.
For number 4?
Yeah.
Yes, I thought we were having a conversation about number 5. I understand that now.
If I waited years. Okay, we talking about
Okay. And hopefully feeling really comfortable.
because what you're doing is finding base of this one and this one, and then multiplying times these two.
I'm good, different.
Yeah, from 2 to 5, that's gonna be the
Right, so
heights.
with the 3.
You okay?
Total bases, if you guys are marking, it's 30. So 30 times 3, we have to divide it by 2.
30, 3 less than 45. And you do it regular.
I need a copy today, so. You need a copy.
Yes, I
What? 30 times 3.
You had it right, 30 times 3, right? You multiply by 1, which is 45. 46.
No, it's not 30, it's 40, because you're adding.
Oh, you add
Right.
it? That's what I meant.
You're doing the trapezoid method,
Yeah.
so it's 1/2. Tell me the base 1, tell me base 2, the first base is a height of 10, the second one is a base height
So,
of
yeah,
30.
I was like 6, so it'd be 60.
I'm just worried because I think you're in subtraction mode too much.
Yeah.
I've been here twice now and I've heard you say subtract. I'm like, no.
I don't do these, I don't do the method. I only do the.
I know you're not using the methods. If you were using the methods, you wouldn't be
I don't use the
subtracting.
midpoint method, which is weird.
Yeah.
Just play more capital.
A.
Yeah.
Why A?
I only use the midpoint method.
The reason I'm good at this is because whenever we were learning
Yep.
it, I didn't think about factoring and stuff, but I always wrote everything out.
Right.
And
So DC is being measured in kilometers. It's always going to be an analysis of those units. It's units for the length times the units for the height. So it's a multiplication that you're going to do. Stephen, what do you have for number 6?
Kind of confusing.
Yep.
Because 4 trapezoids, like this we don't actually.
So that's the thing. You can't. If you read the question carefully, I don't think anywhere in here I said 4 trapezoids of equal width.
I was like, you got.
You get all these data points going from like 0 to like somewhere over here at 11, right? That's what you've got, but I didn't say go from 3 to 14 using 4 trapezoids of equal width. You've got to use the points that you have. And so for each subinterval, you're going to have a different width.